Hello, everyone. Global universities have been engines of innovation and learning for generations. In the US, the research role really blossomed after the Second World War. Many will point specifically to the role of Vannevar Bush, who, as the head of the US Office of Scientific Research and Development during the war, looked after all military R&D. Bush was a visionary, and after the war, he championed the cause of robust public investment in science to support national security. His vision, laid out in his 1945 report to the president, called Science, the Endless Frontier, was to bring together public funding with the educational, scholarly, and service roles of the American university, both public and private. This powered the post-war development of the modern research university and yielded his vast legacy, the powerful, diverse, and highly distributed system of US research universities that dominate and lead the world in innovation, invention, and creative works today. So let's talk about why universities are crucial to our initiative. I'll consider this first by asking, in what ways can the global seed vault be a model for the global microbiome network and the microbiota vault? Under the auspices of the United Nations Food and Agricultural Organization and Biodiversity International, on behalf of the international members of the Consultative Group on Agricultural Research, the CGIAR, the International Treaty on Plant Genetic Resources for Food and Agriculture came into force in 2004. The treaty provides a global system for efforts to enhance global food security through conservation of crop genetic diversity. Work in this direction began in 1993 with the Convention on Biological Diversity, followed in 1996 by adoption of a global plan of action. The Global Crop Diversity Trust, you can find it at croptrust.org, was created also in 2004 to fund and operationalize the treaty and to provide a secure facility, the Svalbard Global Seed Vault, as a global public good for crop diversity storage, protection, and stewardship. This outcome led to the construction and occupancy of a storage vault on the island of Spitsbergen in the Svalbard archipelago of Arctic Norway. The vault was opened in 2008 and today houses over 1 million accessions. I see the Seed Vault as a model of governance and global cooperation second to none. The legal terms governing donation and ownership of accessions and the remarkable subscription by the vast majority of nations to the Seed Vault program are fitting and aspirational models for our work. At the get-go, however, the context in which the Seed Vault was needed and established was quite different than for the Microbiota Vault. First, there are existing hundreds of substantial national and international seed banks worldwide. Notable were national collections in the United States, Russia, England, and China, as well as the CGIAR centers and many agricultural universities and research institutes. There are also notable collections of heirloom crop seeds, amongst them in the US, the Seed Savers Exchange, a nonprofit organization in Iowa. Of course, the large private sector seed companies also hold their own materials, both derived from public seed banks and the result of proprietary breeding and collection activities that they have undertaken. I've read that there are altogether estimated to be more than 1,000 seed banks worldwide. There are likely many more when we count the working collections of public and commercial plant breeders. Rutgers alone holds significant collections of tomato, asparagus, hazelnut, cranberry, blueberry, peaches, thyme, basil, and turf grass seed diversity. So the need to preserve seed diversity was widely understood globally, and many very significant collections were in existence prior to 1993. Moreover, the Crop Trust and the Seed Vault were in a real sense tops-down efforts, with a strong leadership role provided by agencies of the United Nations and the World Bank. It's an important question for us whether and how to gain the international status accorded to the Global Crop Trust. Also embedded, for better or worse, in the crop seed context was the ability to protect seed diversity as intellectual property that the finder or developer could own. While the Convention on Biological Diversity stakes out a case for crop diversity as a public good held in public trust, significant private ownership claims exist, especially in the major food crops. Some of these claims fit within sovereign patent laws, and others are held as trade secrets. And finally, today, we have nearly a century of well-established pathways of use and proven examples of benefits of preserving crop genetic diversity. In an economic sense, both supply and demand for crop genetic diversity have been plain for generations. While not without a variety of tensions along the way, the needs, the demand side, and the supply, the existing collections plus the global vault, developed alongside each other. This I ascribe, at least in part, to the roles of the UN, FAO, and the Crop Trust history. So then, how are global microbiome network and the microbiota vault contexts different? Those of us who sit where we sit and do what we do clearly understand the need for microbiome collection and preservation and the largely absent provisions to meet that global need. However, we are at a relatively new place in the science of the human microbiome and only on the cusp of appreciating the profound importance of microbiomes in human growth, development, metabolism, health, and disease. There is not yet a global appreciation of the need to conserve microbiome diversity, and so we lack widespread appreciation for provision of that need. This is a very different situation than the case of crop diversity and seed banks. The science of microbiomology arose in basic science labs in major universities, mostly in North America and Western Europe. The attraction of the medical communities to microbiomology was fairly quick, again in academic settings, but not immediate and is not complete even today. Knowledge and the capacity to add to new knowledge about how to collect, what to collect, how to store, and how to optimize the use of microbiome knowledge resides in our universities and academic medical centers. Existing know-how and new is rooted in academic science and engineering. It is to such academic expertise, for example, that large pharma companies are turning as they evaluate possible entry into this field. And from such academic institutions that many startup entrepreneurial companies are emerging. Fulfilling the demand for trained scientific and technical personnel to staff the growth of medical, pharmaceutical, and other activities in what will become in time a burgeoning human resource supply chain to support applications of microbiome knowledge remains a primary and undisputed role of the major university. The global vulnerabilities that will drive the need for a microbiota vault differ in many ways from those that drove the seed bank and the global seed vault movements. While it is a vast oversimplification of its roles, the notion of the global seed vault as a doomsday vault, protecting crop diversity in case of a regional or global catastrophe, enabling, if you will, a reboot of agricultural systems, is a real overarching purpose. In the case of microbiota, the global vulnerabilities are in some senses more immediate and more complex. Immediate in the sense of the need being driven by rapid global dietary changes and the uses of antibiotics, for example. Migration, urbanization, hunger, malnutrition are examples of complexities in today's world that also drive the urgency of collecting, preserving, and intensely studying microbiome contents, diversity, and functionalities. Microbiomologists make their collections and maintain working collections in their laboratories. But this is a risky business. Such collections are vulnerable, think tornadoes, typhoons, wildfires, floods, power outages, for example. A global backup vault where the world's microbiota are collected and protected against catastrophes becomes a dire and urgent need as we increase our knowledge about functionalities, as well as our knowledge about how much we have still to learn, what we still don't know about these topics. Dependence on working collections alone is problematic because we can't predict what existing microbiomes that are threatened with extinction might tell us. This point should generate a discussion about whether and how to connect a research unit to the microbiota vault to carry on the kind of meta-analysis, for example, that could yield insights and drive future applied and functionality studies in the university and medical communities. That is to say, in other words, there's a need to build strong pathways of uses and grow understandings of benefits that, in a sense, pre-existed in the crop and seed diversity world. I'd like to close this short lecture with another salient argument, and I'll do this by reciting very briefly important examples of a critical role played by research universities in another context. Barbara McClintock was a plant geneticist educated at Cornell University College of Agriculture in the 1920s, earning her PhD in botany there in 1927. She was elected to the US National Academy of Sciences in 1944 and won the Nobel Prize for Physiology or Medicine in 1983. From study of maize mutations revealing easily scored phenotypes, she discovered the existence of transposable elements. She called them controlling elements. The Nobel work was completed at Cold Spring Harbor Lab, where she moved in 1944 out of frustration with her limited faculty career options at the University of Missouri. Her pathway to Cold Spring Harbor was through a position at Columbia University. Lynn Margulis was the pioneer in the study of speciation and evolution that led to the hypothesis, now proven science, of endosymbiosis. She was educated at the University of Chicago, the University of Wisconsin-Madison, and the University of California at Berkeley. Her entire career was spent as a university faculty member at Brandeis, Boston University, and the University of Massachusetts Amherst. For most of her career, her work was highly controversial. But in addition to published science, she also wrote books that appealed to lay readers. In time, her work went from being considered crap by one grant application reviewer to comparison with Charles Darwin. And I quote Jan Sapp, the historian, Lynn Margulis's name is as synonymous with symbiosis as Charles Darwin's is with evolution, unquote. Rita Caldwell graduated from Purdue University and earned her PhD from the University of Washington in Seattle. She is an environmental microbiologist who was also trained in oceanography. With global collaborators, she led studies that described the life cycle and deduced the mechanisms of pathogenesis of Vibrio cholera. Still active in her mid-80s, Rita is a longtime member of the faculty of the University of Maryland College Park and has also had appointments at the Bloomberg School of Public Health of Johns Hopkins University and at Georgetown. She was the 11th director from 1998 to 2004 of the US National Science Foundation. She is the author of many books, the most recent in August 2020, of which is, quote, A Lab of One's Own, One Woman's Personal Journey Through Sexism in Science. I strongly recommend this book to you. So why have I taken you on this short joyride of science careers embedded in research universities? There are several points illustrated in these stories, not the least about the limitations imposed and the struggles required to overcome them. But the salient and seminal point is this: research universities have played an enormous role in liberating women into science careers. We are working to build not just a network, not just a vault, but also related new career paths. At the beginning, now, let's pause a moment to solemnly pledge that the career paths we will enable and the institutions we will build will be gendered and in all other ways inclusive, diverse, and equitable, including those of Indigenous peoples and the dispossessed. This is work that research universities are uniquely capable of doing and are finally taking full responsibility for. In summary, I believe that the roles of universities in the future development and collection of microbiota to fuel and protect the future of microbiomes is central, crucial, and essential. This is what we are gathered to discuss, plan, and plot. If not now, when? If not us, Who? And if not at universities, where? Let's get moving. Thank you.